Okay, Assalamualaikum and good evening, everyone. Alright, so we want to proceed with our next chapter, which is here elementary problem in the calculus of variation. So before this, we have done with understanding the terminologies and basic of calculus of variation. Now we want to find what is the problems that we want to solve in calculus of variation. Alright, so before that, we need to do this assumption. Okay, we let the function of fx, y, and y prime have a continuous partial derivative up to order 2 inclusive with respect to all arguments. Right, so as you can see here, we have a function of f, x, y, and y prime. So this is actually a function of x, y of x, and y prime of x. So this is a function y of x, and this is a function of y prime of x, and this f here is a function of y and y prime and x, right? So let this function have continuous partial derivative up to order 2 inclusive with respect to all arguments. So these arguments here is referred to the variable inside this function of x, yx, and y prime. So what is the problem that we want to solve here? The problem here is from amongst all the functions of yx, having a continuous derivative and satisfying the boundary condition ya equals to a and yb equals to b, we want to find the function which give the functional here j a relative extremum. So this relative extremum means the minimum and also the maximum. Okay, we want to find the function which give this functional a minimum or a maximum. Alright, so we call it as a relative extremum. Okay, so from this ya and yb here, we call it as a boundary condition. We want to find the function which give this functional a relative extremum. So that is the problem that we want to solve. So alternatively, it is a problem of finding the relative extremum on the functional here j on the set of all smooth curve connecting two given points of P1 and P2. Alright, let's say we have curve y1, y2, and y3. Okay, so amongst all this function of yx which have a continuous derivative and satisfy the condition from point A to point B, okay, we want to find which functions here which give the functional j a relative extremum. So amongst this function, we want to find which function that give this functional a relative extremum. So in other words, we want to find the relative extremum of this functional. Okay, now, so in order to find the relative extremum of the functional, we have the first theorem here, which is Euler's equation. All right. For the functional, okay, let's read it first. For the functional 2, where this is the functional 2, for the functional jyx, here defined on the set of function y equals to yx, having a continuous first derivative and satisfying the boundary condition 1, where this is your boundary condition given in 1, alright, to attain an extremum on the given function yx, it is necessary that this function satisfy the Euler equation, where fy minus derivative of fy prime with respect to x equals to 0. So this is Euler equation. Okay, so this Euler equation is the necessary condition in order to find the relative extremum. All right. Okay, so let's try to prove this Euler equation. What is the relation of this Euler equation in order to find this relative extremum? Okay. Okay, so before that, let's revise again what we have learned in our previous topic. Okay, so in our previous topic, there are a necessary condition for an extremum. All right, where in order that condition to be an extremum, we have to make sure that this delta j goes to 0. What is delta j here? Where this is the first variation of functional. Alright, so this delta j equals to 0. This is necessary condition for an extremum, and this Euler equation is the necessary condition for this relative extremum, means that these two. Okay, so now let's prove this. Alright, so we have variation here. Alright, so in order to find the variation, what we need to do is to find the increment of a functional. Alright, so remember the functional given here is jyx equals to integrate from a to b of f x, y, and y prime. Okay, so this is a functional of x, y, and y prime. Now, in order to find the first variation here, we need to find the increment first, where the increment of j is given by jy plus delta y minus jy. Okay, so referring to the functional here, now this increment of j become integrate from a to b of fx. Okay, x remain x because this increment consists of y. So now this y now becomes y plus delta y. And this y prime now becomes y prime plus delta y prime with respect to x, minus with a functional of y. So we have integrate from a to b of f, x, y, and y prime. Integrate with respect to x. Okay, so this is your first step. Right. Alright, so our next step here, now we have an integrand of fxy plus delta y prime plus delta y prime minus integral from a to b of fxy y prime. So this is quite a challenging for you to expand, and we need to use a Taylor series expansion of multi-variable. Alright, so in order to expand this, we need to expand by using Taylor series expansion of multi-variable. Right, okay, so this is the definition of Taylor series expansion of multi-variable here. Alright, we have fxy. Now, by using the points of a and b, so the expansion becomes like this. Okay, fxy becomes fab, fxab x minus a. Alright, so now we change the value of xy here with y and y prime. Alright, now looking at this, fab becomes the function itself. So we have ab in terms of y and y prime. So this is fab, alright? Okay, plus with fxab x minus a. So your x here is y. So this is fy. Okay, ab is fxab is the original part of the functional. Now x minus a. So looking at this, your x is here. Okay, so your x is y plus delta y. So y plus delta y minus with a. So this is your a, y, and b is your y prime. Okay, so x minus a plus with what? The next one is fy, ab, y minus b. So your y is y prime. Okay, so fy prime. Alright, and then AB x y prime, y minus b, y minus b, y is y prime plus delta y prime. So this is your y minus with b. Okay, and then plus with half fxxab. So half xx here is what? y. So y, ab, x, y prime, x minus a squared. So x is y plus delta y minus with a, y. So this one will become delta y squared. Okay, and then the next one is plus with fxy. X is y is y prime. So that's why this one becomes fyy prime. xab, xy prime, x minus a, y plus delta y minus ay. So this is delta y. And then y minus b, y is y prime plus delta y prime minus with by prime. So this one becomes delta y prime. And the next one here is fyy. So your y is y prime. So fy prime y prime. abx y prime times with y minus b squared. So y is y prime plus delta y prime minus with by prime squared, and this will become delta y prime squared. Okay, and then don't forget this part, the second part here, minus with integral of a b f x y prime. All right. Okay, as you can see, it is expanded. So we try to simplify. All right. So here we have integral of a b f x y prime. This one also. Then we can eliminate these two. Okay, and then this one will left you delta y prime, delta y only. This one delta y prime only. This one becomes delta y squared. This one becomes delta y prime, and this one is delta y prime squared. So now it is simplified. So what is our next step? Okay, so our next step is to find the variation. Right, so remember we want to find the variation of the function. First we have to find the increment. Now we expand this increment. That our next step is to extract the linear term. Of increment j, so that we can find what is your variation of j. Here consists of y and y prime. Okay, so as we can see, we want to extract the linear term here. We need to find only the linear part. So this is eliminated already. This one is delta y. Okay, this one is delta y prime, still linear. This is delta y squared, not linear. This is delta y prime, delta y, not linear. And this is delta y prime squared. So we have these two as a linear term of increment j. So we have fy, xy, y prime, delta y, plus with fy prime, x, y prime, delta y prime, and remember the integral ab here. Okay, integrate with respect to x. Okay, as you can see here, we have delta y and delta y prime. Now, we want to further simplify this expression and we try to omit the delta y prime here. So what we need to do is to integrate this part by using integration by parts. So as you can see from this, okay, we integrate fy prime, xy, y prime, delta y prime here with integration by part. Alright, okay, so from here you determine your u as your fy prime and your dv as your delta y prime here. Okay, we just write down the fy prime and delta y prime in order to simplify the process. And then proceed with the integration by part. We have your u and dv. So from this you differentiate and you get dx. Dx of fy prime because you differentiate this fy prime with respect to x. And this dv is equal to delta y prime dx, and when you integrate dv, you just put the antiderivative of delta y prime here. Now it becomes delta y. So once you get your u, v and dv, substitute back to the original function that you obtained here. So now you have integral from a to b of fy, xy, y prime, delta y plus with uv minus with integral of v du. So here we have the simplified version of the post-extract linear term here, where we have the simplified version of variation of j in y and y prime. Alright? Alright, then remember what we need to find is to find the extremum among functions. So we have, alright, so we have lots of function. Okay, from a to b, we have multiple function and we want to find the extremum in order to find the extremum of the functional. Alright, so let's say we have point A and point B. So the variation here is happen among points from A to B, not in the points of A and B here. So it lies everywhere from A to B, in between A to B. So if you have a z value of A and B here, means you substitute A and B in the function, then it is not a variation. So we just can put this as 0. There is no variation. Delta y is 0. Okay. So from here we can simplify this to a, integrate from ab of fy delta y minus ab d over dx fy prime delta y dx. So here we can factorize this, put integral of ab delta y outside. So we have fy minus differentiate of fy prime with respect to x and dx here. Okay, so this is variation of delta y. Now looking at this figure, okay, this delta y cannot be 0 because there is a variation along the line of each functions of y. So in order to this variation becomes 0, means that we need to equate fy dx here with 0. So this is where the Euler equation comes from. Okay, why this one cannot be 0? Because there is a variation along the lines from A to B, but there is no variation at point A and B. So that's why this delta y is 0. But now this delta y cannot be 0. But in order to the first variation equals to 0, so we need to equate this to 0. Then we can prove that this Euler's equation. Okay, where this is the necessary condition for an extremum. Alright, so please remember this Euler equation that we're going to use for the rest of the topics after this. Okay, so this equation can be expanded to second order differential equation, as you can see from your notes. Alright, let me paste it here. Okay, so this equation can be expanded to this. The integral curve of this Euler equation are called extremum. Then this equation can be expanded to the second order of differential equation here. Alright, I don't have to show this. Otherwise, it will get you confused more and more. Okay, so now from this equation, where this is a second order differential equation, okay, so this general solution must depend on two arbitrary constants. The values of these constants are determined from the boundary condition. The first condition that have been mentioned previously, which is this one. Okay, then now the problem of these Eulers becomes the boundary value problem. So the extremum of the second can only be realized on those extremum which satisfies the condition. The extremum of the second equation, what is second equation previously, which is the functional of J. Okay, can only be realized on those extremums which satisfy the first condition, the boundary condition here. Okay, so the boundary value problem 5 here does not always have a solution, and if a solution exists, it may not be unique. So now let's proceed with applying this Euler's equation and the boundary condition to find the extrema. Okay, let's move forward to the example. Alright, so let's move forward to the example. Now we want to find the extremals of the following functional. Alright, so the first one here, the functional j is given by integrate from -1 to 0 of 12xy minus y prime squared x, where the boundary condition is given here, -1 and 0. Okay, point x equals to -1 and x equals to 0. Alright, so now remembering the Euler's equation of fy minus delta derivative of x of fy prime equals to 0. Alright, so your first step here is to identify what is your f. Okay, so as you can see from here, it is a combination of x, y, and y prime. So this is a function of x, yx, and y prime x. Or we can simplify write this as fx, y, and y prime. So this f is equals to 12xy minus y prime squared. Why we just take this as your f? Remember? Okay. Remember in our previous topics where the problem that we want to solve is to find the function which gives the functional j here relative extrema. So as you can see, the functional j is given by integrate from a to b of f. So this is your f. So from here you can say that your f is 12xy minus y prime squared dx. Okay, so your second step here is by Euler's equation, we want to find fy minus derivative of x, fy prime equals to 0. So here you have 12xy minus y prime squared. So fy means differentiate f with respect to y. So we apply the partial derivative here. So means that the rest other than y is a constant. So fy here will be 12x, right? And then we can find what is your fy prime. So your fy prime is differentiate for variable y prime. Here you have minus 2y prime. Okay, so substitute to the Euler's equation. We have fy 12x differentiate with respect to x of fy prime negative 2y prime equals to 0. So here 12x differentiate negative 2y prime will give you negative 2y double prime. Why? Because this y prime is actually a function consists of y prime x. So differentiate y prime x with respect to x, you will get y double prime. So from here you can simplify, you get 12x plus 2y double prime equals to 0. 6x plus y double prime equals to 0. That's why from this Euler's equation we can find that we want to find the solution of second derivative. Okay, second order of partial derivative. This is where the solution of partial differential equation is to be found. All right. Okay, so from here we want to find the solution of this second order differential equation. All right, so sort this, put y double prime to the left hand side. Now it is equals to negative 6x. So this is linear second order of non-homogeneous differential equation. Why it is non-homogeneous? Because your right hand side equals to function of x. If your right hand side equals to 0, then we say that it is homogeneous. Okay, so in order to solve the partial derivative here, so your first step is to identify what is the solution of differential equation where we have yh plus with yp. Okay, so from yh here, as you can see, we have y double prime equals to 0, means that your characteristic is m squared equals to 0. Remember, you have learned this. So m equals to 0. All right, and then yh is given by exponent x, a plus bx, and your exponent mx, a plus bx, and given m is 0, so yh is exponent to the power of 0, a plus bx, and your yh is equals to a plus bx. All right. So next, what is your yp? All right. Okay, so given yp given here equals to x to the power of r c plus dx, because okay, cx plus d. Okay, why? Because we have negative 6x. Here is a linear equation. Okay, so we have to test when r equals to 0, then your yp equals to cx plus d. Look at your yh. We have dx, so we cannot use the same identical function here. So move forward when r equals to 1. Yp equals to cx squared plus dx. Still we have x here. Alright, so move r equals to 2. Yp equals to cx cubed plus dx squared. Okay, so now comparing this yp to y double prime here means you need to differentiate up to second order. So yp is given cx cubed plus cx squared, right? So your y prime equals to 3cx squared plus 2 dx y double prime equals to 6cx plus 2d. So here we have y double prime, here we have y double prime, then we can just compare. So compare to negative 6x here. So now you can see c becomes negative 1 and d becomes 0. So your yp equals to negative x cubed. Okay, so from here you can say that your general solution of y equals to yh plus yp now becomes a plus bx minus x cubed. Okay, right, so remember this is general solution. We're not finished yet because we have this condition. Okay, remember we can use the condition given in order to obtain the values of constant a and b here. Okay, okay. Looking at this, we have boundary condition given here. Okay, so when x equals to negative 1, then y equals to 1. When x equals to 0, then y equals to 0. By applying this condition, you have y equals to a plus bx minus x cubed. Okay, so substitute here when x equals to 0, y equals to 0. Then your a equals to 0. Okay, and then when x equals to minus 1, y equals to 1. So you can say here a minus b plus 1 equals to 1. A is 0, then minus b equals to this one 0, b equals to 0, and your solution y equals to negative x cubed. Okay, so this is what we call extremum. So remember the solution, the problem here, find the extremals of the following functional, then you get y equals to negative x cubed, then it means that this y equals to negative x cubed is the extremals of the functional j yx here. Okay, so that's it. This is how you find the extrema. Alright, so I hope you enjoy it and please try the second example here. Okay. Alright, so by following the step here, first thing first, you need to identify f, and then following the Euler's equation and find the extremals using the condition given. Alright, okay, so that's all for today, guys. Thank you.